Stop scrolling for a second, because this is going to sound wrong, but it isn't. A black hole does not care about what's inside it. Yeah, think about that. Everything you've seen, movies, animations, even textbooks, show stuff falling into a black hole, like there's some deep interior where everything ends up. But physics, real physics, is starting to say something else. It says, the surface is enough? And if that's true, then everything you think about inside might just be a story. If that kind of idea scratches your brain a little, stay. And yeah, subscribe. This channel is for slow thinking, not quick noise. Let's go back. Before all this weird stuff, black holes were simple. Brutally simple. You take a massive star. It collapses under its own gravity. No force strong enough to stop it. It shrinks and shrinks and shrinks until space-time itself gives up. And what you get is a region where gravity is so strong that nothing escapes. Not even light. That boundary, that point of no return, is called the event horizon. Cross it, and you're done. That was the picture. Clean. Scary. Final. And people thought, okay, whatever falls in, stays in. Makes sense. You throw in a rock, it's inside. You throw in a book, it's inside. You throw in a whole planet. Guess what? Inside. End of story. But physics doesn't like endings like that. Especially quantum physics. Quantum theory has this rule, and it's not optional. Information cannot be destroyed, not hidden, not erased, not lost forever. You can scramble it, sure. You can mix it up so badly it looks gone. But deep down it's still there. Always. So now we have attention. Black holes seem to erase things. Quantum physics says that's illegal. So something is off. Let's make it real. Imagine you take your phone, all your photos, messages, notes, everything, and you drop it into a black hole. Now ask yourself, where is that information? Not the phone, not the metal or glass. The information, the pattern, the data. Is it gone? If the answer is yes, then quantum mechanics breaks. And if quantum mechanics breaks, a lot more breaks with it. Because quantum theory is not some small side idea. It's the base layer of everything we understand about particles, atoms, chemistry, you name it. So we can't just throw it away. This problem sat there for a while. People knew it, but nobody had a clean answer until something unexpected happened. Stephen Hawking looked at black holes and found a crack. Not in the math exactly, but in the behavior. He showed that black holes are not perfectly black. They emit radiation, very faint, but real. This is now called Hawking radiation. And this changes everything. Because if a black hole emits radiation, then it can lose energy. And if it loses energy, it can shrink. And if it keeps shrinking, it can disappear. Let that sink in. A black hole is not forever. It can evaporate. Now the problem explodes. Because if the black hole disappears and everything that fell in is gone, then information is truly lost. Not hidden, not scrambled, gone. That's a violation of quantum mechanics. A serious one, not a small glitch. So now physicists are stuck. Either 1. Black holes destroy information quantum theory is wrong too. Information is preserved something about black holes is wrong, pick your poison. And for a while, nobody knew which one to give up. This is where Leonard Susskind enters the story. And instead of choosing one side, he questioned the assumption itself. He asked, why are we so sure the information goes inside? That's the key shift. Not how does it come out, but does it ever really go in? At first, it sounds like wordplay, like trying to escape the problem with clever language. But it's deeper than that. Because when you look carefully at the math of black holes, you find something strange. The amount of information a black hole can hold is not based on its volume. It's based on its surface area. That's weird, because in normal life, storage depends on volume. A bigger room holds more stuff than a smaller room. A bigger hard drive holds more data. Everything scales with volume. But black holes don't follow that rule. Their storage capacity scales with the area of the event horizon. Just the surface. Nothing about the inside. That's not a small detail. That's a clue. A big one. It's like finding out your entire computer's memory depends only on the size of the screen, not what's inside the box. You'd stop and go, wait, what? So Susskind and others started thinking, maybe the surface is not just a boundary. Maybe it's where the information actually lives. And that idea, slowly, becomes something radical. But we'll get there. Because first, we need to understand why the surface matters so much. Here's a way to feel it. Imagine the event horizon as a kind of skin. Not a physical surface you can touch, but a mathematical one. Still, it behaves like something real. Every tiny patch of that surface can store a bit of information. Not much, just a tiny amount, but there are many such patches. And together, they add up. Now here's the twist. No matter what falls into the black hole, the total information it can hold is limited by that surface, not by how much stuff you cram inside. So even if you throw in more and more, the capacity doesn't grow with the interior. Only the surface. This flips our intuition. We think the inside should matter most, but the equations say it doesn't. Let's pick up right where it starts to feel uncomfortable. We said something strange. A black hole stores information based on its surface, not its inside. Now let's not rush past that, because this is where most people nod, but don't really process it. Think about a sphere, a ball. It has volume, the inside space, and it has surface area, the outer skin. In everyday life, volume is what matters. If you want to store water or air or anything physical, you care about volume. But black holes ignore that. They behave like only the surface counts. So physicists asked, what if this is not just a weird property, but a principle? This leads to something called the holographic principle. And yeah, the name sounds fancy, but the idea is simple. A hologram is a flat surface that contains a 3D image. Not an illusion exactly, but a full description of depth stored in 2D. Now imagine that idea applied to physics. Everything inside a region of space could be described by information on its boundary. Not inside, on the edge. Let that sit for a second, because it's not just about black holes anymore. It's about space itself. Back to the black hole. When something falls toward it, from the outside observer's view, it never quite crosses the horizon. It slows down, more and more. Time stretches. Light redshifts. So what you see is this. The object gets closer to the surface, but kind of freezes there. Fades, but never fully disappears. So from that perspective, the information never really goes inside. It gets smeared over the surface. Encoded there, not in a neat way. Not like a file on your computer, more like a scrambled pattern, but still present. And that matters. Because if the information stays on the surface, then when the black hole evaporates, that information can, in principle, come back out. Not in the same form, not as the original object, but as correlations in the radiation, subtle patterns. So nothing is lost, just transformed. And suddenly, quantum mechanics is safe again. But there's a cost, a conceptual one. We have to give up the idea that the inside is where the action is. Let's make it more personal. Imagine you're the one falling in. From your perspective, you cross the horizon without noticing anything special. No wall, no shock. You just keep going. But from the outside, you never quite make it. You get stuck at the edge. Two different stories, both valid. This is what we call complementarity. Reality depends on the observer, not in a vague way, but in a precise, physical sense. Now here's the tension. If the information is on the surface, and you feel like you're inside, then what is inside really? Is it a real place? Or is it a kind of emergent story? That's not a small question. Because if the inside is not fundamental, then maybe space itself is not fundamental. Think about that. We treat space like a stage. Things happen in it. But maybe the stage itself is built from something deeper. And that deeper thing might be information. Not information like text or images, but more basic. Patterns, relationships, structure. And the surface is where that structure lives. So the black hole becomes a hint, a clue, a system where this deeper rule becomes visible. Normally, in everyday physics, we don't notice this, because the effects are too small, too subtle. But black holes push things to the extreme. And when you push physics hard enough, it shows you its hidden rules. So now we're looking at a new picture. Not things go inside stored in volume, but things approach the surface encoded on the boundary. That's a shift. And it's not easy to accept, because it goes against how we experience the world. We move through space. We feel depth. We think in terms of inside and outside. But physics is saying that might not be the fundamental layer. Now we take the step that feels almost too big. Up to now, we were talking about black holes. Weird, extreme, rare objects. Easy to keep them in a box. But the logic doesn't stay there. It leaks out. If a black hole stores information on its surface, why would that rule apply only there? Why not everywhere? That question leads to something bold. Maybe the entire universe follows a holographic description, not as a metaphor, as a real, working framework. There's a theory, well, more like a duality, called ad/CFT. The name doesn't matter much here. What matters is what it says. It says you can describe a full gravitational universe with all its depth and curvature using a theory that lives on the boundary. No gravity there, just fields. Two different descriptions. Same physics. One has volume, one has only surface, and they match. That's shocking, because it means gravity, space-time, all of it, can emerge from something lower dimensional. So now go back to the black hole. It's not just a strange object. It's a training ground, a place where this idea becomes unavoidable. And if that's true, then space is not what we think. We think of space as continuous, smooth, always there. But maybe it's built from discrete bits of information, like pixels, and the inside we experience is just a reconstruction, a kind of projection, not fake, but not fundamental. This is where things start to feel slippery, because your intuition doesn't help much here. You can't visualize it easily. You can't point to it. But the math keeps pushing in that direction. Let's ground it again. Imagine a screen. On that screen, a full 3D world is being rendered. Characters move, objects interact, depth appears real, but everything is encoded in 2D pixels. Now imagine you're inside that world. You wouldn't see the pixels. You'd experience depth. That's the kind of idea we're dealing with. Not saying we're in a simulation. That's a different claim. This is about how information is structured, how reality is described, and black holes forced us to see it, because they broke the old rules. They forced us to ask, where is information stored? What is space made of? And the answers are not what we expected. So now the phrase inside a black hole starts to feel less solid. Because if everything is encoded on the surface, then the inside is not where the fundamental data lives. It's like a story that emerges from that data, and that doesn't make it unreal, just secondary, like temperature. Temperature is real. You feel it, but it's not fundamental. It emerges from particle motion. Maybe space is like that. And if space is emergent, then what about you? That's not a poetic question. It's a physical one, because you exist in space. Your body has shape, volume, position. But if space itself is emergent, then your inside might also be not fundamental. That's a hard thought, and we won't pretend to solve it here. But we can follow the direction. Black holes, surface, storage, holographic, principle, emergent space, and now we're here, at the edge of what we can comfortably understand. So here we are. We started with a simple idea. Things fall into black holes. They go inside. They're gone. And now, that idea doesn't feel so solid anymore. Instead, we have something stranger, something quieter. The black hole doesn't need an inside to store what it knows. The surface is enough. Everything that falls in, every detail, every structure, gets encoded on the edge. Not in a way we can easily read. Not like files in a folder. But it's there. And over time, as the black hole evaporates, that information leaks back out. Not as the original object, but as subtle patterns and radiation. So nothing is truly lost, just transformed. And that's the key. We had to give up something to keep that truth. We had to give up the idea that the inside is fundamental. Now let's sit with that. We are used to thinking, inside equals real, surface equals boundary, but black holes flip it. Surface equals where information lives inside equals maybe an emergent picture. And once you see that, you start noticing it everywhere. Edges matter. Boundaries matter. Interfaces matter. Even in everyday life. A screen shows you a world, but the depth you see comes from patterns on a surface. Your eyes receive light on a 2D surface, the retina, and from that, your brain builds depth. So even your perception already works like a kind of hologram. That doesn't prove the universe is holographic, but it shows we shouldn't trust intuition too much here. Now bring it back to black holes. When physicists say the black hole knows its surface, they don't mean it literally thinks. They mean the equations, the real bookkeeping of nature, only depend on the surface. That's where the information is counted. That's where entropy lives, not inside. And that's a big shift, because entropy is not just a number. It's a measure of information. So when entropy depends on area, it's telling you something deep. It's telling you where the information is. And it points again and again to the surface. Now here's the part that lingers. If black holes work this way, and if the universe follows similar rules, then the distinction between inside and outside might not be as fundamental as we think. It might be a useful description, a convenient one, but not the base layer. And that changes how you see things. Not in a dramatic, movie-like way, but in a quiet shift. You start to wonder, where is information really? What is space made of? What is inside actually describing? And you don't get clean answers. Not yet, but you get better questions. And that's where physics lives, not in final answers, but in sharper questions. So next time you hear someone say, everything falls inside a black hole, you can pause, just a little, and think, maybe not. Maybe it never really leaves the surface. Maybe the edge is enough. And maybe the edge is where everything actually begins. If this made you slow down and think, subscribe. This channel isn't about rushing to conclusions. It's about sitting with ideas until they start to feel real.